Right. So we are saying that this will correspond to the complex scalar corresponds to not one but two degrees of freedom. So at each point in momentum space, there will be two harmonic oscillators, not one. And therefore, in the field, you will get two different creation annihilation, two sets of creation annihilation operators. And these creation annihilation operators BP and CP correspond to the two different harmonic oscillators that are there. So this is BP, one harmonic oscillator, and CP dagger for the other harmonic oscillator. This is the convention of writing, how we write PP and CP dagger. And similarly, psi dagger is just the complex conjugate of this. So take dagger, you will get CP with e to the minus IP dot x and PP dagger with e to the IP dot x. And I may wonder why is there two different things, PP and CP dagger. This is again because I have two harmonic oscillators, and to see it more explicitly, we can go back to this formula that I wrote, that I can write this as in terms of two real fields, and you can check that if you substitute in the equations of motion, that both this real and imaginary part of psi will satisfy the Klein-Gordon equation. So they will have exactly the same kind of expansion as a Klein-Gordon field, and there are two of them. So phi real we call the creation annihilation operators AP, and phi imaginary we can call them some DP. And so when I put this psi back together using this, I have one term which has AP plus IDP, and another term which is AP dagger plus IDP dagger. And now you see that these two terms are not complex conjugates of each other because there is I here. So complex conjugate would be AP dagger minus IDP dagger, but this is plus. So these are two separate independent operators, and one of them I call BP and the other I call CP dagger. Okay, this I can always do. So this is the origin of getting two different operators here. And now that we have this kind of AP, these guys, we obviously have for each of these guys we have formula like AP B prime del P minus P prime. Similarly for DP DP prime, and using those we can find the commutation relation for the BPs. So for this BPs, we will get this, and all the commutation relation between BP and CP, these two different operators which are independent of each other, those two different oscillators which are independent of each other, they will all give zero commutation. So they are independent, they don't commute with each other. Okay, so this is what we have. It's basically a double of the previous theory. Now Hamiltonian for the Klein-Gordon case was this AP dagger AP, and Hamiltonian for this, if you go through all the steps starting from the Lagrangian, etc., etc., and this I will leave as a homework for you. Homework. You find that this is the result, that as you would expect. There are two oscillators, so there is a term corresponding to each oscillator. Okay. Now there's a symmetry in this system. There's a symmetry in this Lagrangian, and this symmetry is that if I take psi and if I multiply psi with some factor e to the power I alpha, then the Lagrangian will remain invariant, or the action will remain invariant. And this you can check because the Lagrangian looks like this, and this second term is mod psi square. So when we take psi to e to the power I alpha psi, then psi star goes to e to the minus I alpha psi star, because this is a complex conjugate of this. Just taking complex conjugate from here, you get this. And so if I consider psi into psi star, which is mod psi square, there's a e to the power alpha coming from psi and e to the minus I alpha coming from psi star, so which cancel, and this doesn't change. Very similarly for the first term, I have del mu e to the minus I alpha psi star, del mu e to the power alpha psi. Alpha is taken to be a constant, so it goes outside, and it will be minus I alpha, and alpha cancel, giving me once again the same thing. So the Lagrangian does not change under this transformation of the field. So this psi going to e to the power alpha psi is a symmetry of the action. And if you remember, we had learned that for every symmetry there is a conserved quantity. Like for time translation there is energy, for space translation there is momentum. We said that for every symmetry there is a conserved quantity, and there is a procedure of constructing such a quantity if you know the Lagrangian, which we did not go into, but it's known as the Neutert procedure. It's sufficient for you to know that such a procedure exists, and if given the Lagrangian and a symmetry, you can always construct a conserved quantity from it. But here I will just tell you what the conserved quantity is. It is this Q, which we call a charge, which has this kind of formula. Okay, this is psi star psi dot minus psi dot, something like this, and then, or is it del psi? Anyway, I think it is this, and the point is you can prove that dq dt is 0. So the time variation of this charge is 0, meaning this is conserved charge. Okay. So again, if you make those substitutions in terms of the dagger operators and so on, you will finally get this charge in terms of the creation annihilation operators, and it will look like this: Bp dagger Bp minus Cp dagger Cp. Okay. And now what we can show is that if I take the action of this operator Q on a state which has, so we have these two kinds of oscillators here, Bp and Cp. So corresponding, we will have two different kinds of particles. When Bp dagger acts on this 0, I get a B particle. When Cp dagger acts on this, I get a C particle. So there are two B and C particles, and Q is something that can help us distinguish between them, because Q acting on Pb, because this term is plus, comes with a plus sign, acting on Pb will just give Pb, it will just return Pb. But Q acting on a C particle momentum eigenstate will give me minus Pc. So this B particle momentum eigenstates are also eigenstates of Q with eigenvalue plus 1, and these are eigenstates of Q with eigenvalue minus 1. So if I measure Q, I'll get plus 1 here, minus 1 here. So Q is called a charge for reasons that we don't need to get into. Let's just go with that name. So the B particle has a positive charge, and a C particle has a negative charge. And we don't use the terminology B and C particles. What we call them are particles and antiparticles. So B, if we call B as the particle, the one with the positive charge, let's call that the particle, and C is the antiparticle of B. So it has the opposite charge. So generally a particle antiparticle will have opposite quantum numbers. Whatever quantum numbers are there, the quantum numbers will be opposite. So things with opposite quantum numbers but mass the same mass but opposite quantum numbers, they are particle antiparticle pairs. So B and C form a particle antiparticle pair. Of course, it's convention which one you want to call particle, which one you want to call antiparticle. We are calling the B's as the particles. This is just convention. Okay. So again, to recap what we did, there is a charge operator, and this is a conserved quantity. So this is the only conserved quantity here in this theory, apart from the Hamiltonian, etc. And this, for this conserved quantity, B and C particles have opposite charges, and so we consider them to be a particle antiparticle pair. Okay, good. So now we will see there's an interesting relation between particle antiparticle pairs which comes under time reversal. So remember, you may remember from quantum mechanics, your time reversal was an anti-unitary operator. So when I consider time reversal on some I, it gives me minus I. So if we take time reversal of some field operator phi, sorry, we call it psi, we should get psi of minus t x dagger. So it's anti-unitary. So first of all, it changes the time, and also it gives me a dagger here. Okay. So the action of this gives me dagger, and also remember that when it acts on the momentum eigenstate, it should reverse it, because if this is going positive in time, time reversal should give me a something that is going backwards in time. So the momentum must also reverse. If it was going this way, if I run the tape back, then I will see the particle going in the opposite way. Okay, so now this becomes interesting for causality. And here what we can do is we take this action of t acting on this, and we leave this as an exercise, which is kind of partly worked out here, where you take time reversal of this. So you act with this using the definition of time reversal which I gave here, which is psi minus t x dagger. So you take t, which is x naught here, to minus t, and also you take complex conjugate, and then what you get is b minus p dagger and c minus p. So this is what you get. Okay, so these are the things that you get. So you see that if I consider these two terms, if I compare them, then I see that under time reversal, Cp dagger, which was the coefficient of e to the power I p dot x term, is getting mapped to the Bp dagger. So Cp dagger, sorry, B minus P, this is minus here, and this is minus here. Cp dagger goes to B minus P dagger, and Bp goes to C minus P. What does this mean? So if I consider a Cp dagger particle 0, this is a P dagger particle. If I time reverse it, if I time reverse this particle, so if I, sorry, whatever it dagger, so this is a C particle, which in our notation, sorry, let me do it this way. Let me consider B particle, Vp dagger 0, it's the same thing. This is a P particle, and under time reversal, this becomes a Vp dagger goes to C of, it will go to C of minus P dagger with a minus sign. So this will become a C particle with opposite momentum, which means this was a particle, and time reversal makes it an antiparticle moving in the opposite direction. So if this was a particle moving forward in time, if I do a time reversal, if I run the tape in the opposite direction, run the film in the opposite direction, it will look like an antiparticle going backwards in time. And similarly, if I have a particle going forward, antiparticle going forward in time, and if I do a time reversal, it looks like a particle going backwards in time. Okay, and this gives an interesting interpretation to causality. So again, here also we have causality, which is given by this relation, psi dagger psi commutation vanishes, and then you can do the calculation the same way, and you will find that there has to be a cancellation between 0 psi dagger y psi x. Again, you are proving this is your problem, and minus psi x psi dagger y. Now these two things have different interpretation here. So psi x 0 when psi x acts on 0, what remains is the CP daggers, because remember psi x has BP and CP dagger. So BP acting on 0 gives 0, CP dagger acting on 0 gives antiparticles. And similarly, the opposite is psi dagger going to 0, acting on the bra vector 0, and this is given by there's a BP in the psi, and this is CP dagger. And so psi dagger is the dagger of this whole thing, so it has BP dagger and CP. BP dagger kills this, CP remains. So this gives me the probability of antiparticle being absorbed at a point or reaching a point y. So what this whole term, the interpretation of this whole term, is the amplitude of antiparticle going from x to y. And likewise this term, which is the opposite, it has dagger here and not dagger in the first part, this will have, you can check, the interpretation of an amplitude of a particle going from y to x. So this will be antiparticle going from x to y and amplitude of particle going from y to x. So now suppose I am considering again some frame where there's a person who is saying that okay, there has to be in the frame where x happens before y. So here we have in some frame where y happens later, x happens before, and so this guy will say there's an amplitude of this particle going from y to x, sorry, x to y, and so there's an amplitude of the particle going from x to y, and similarly there is an amplitude also of the antiparticle going from x to y. So there's amplitude of particle going from x to y, and there's an antiparticle which can go sorry. So what we have is, when we look at, forget about this, when we are looking at the commutator, the two terms that are cancelling, which is this and this. So what are these terms? One is the amplitude of the antiparticle going from y to x, so amplitude of the antiparticle, which is c, going from x to y, minus amplitude of the particle going from here, this is y is there, so amplitude of the particle going from y to x. Okay, so this is the commutator. So this is the commutator, psi, my bad, psi dagger x, psi y, 0. This is this. This can be interpreted as this. Now consider a situation where y happens later from x. So we have, for this person, the space-like separators, I can go to a frame where y is happening later. So in this frame, I have this quantity which is x goes to y, and I have this, this is a b, particle going from y to x. And now what we can consider is that the time lag separated, so this goes to this for this observer, and this goes to this. But remember that we just saw that particle going forward in time is the same as antiparticle going backwards in time. So for this person, the interpretation of this is particle going from x to y, which is particle going forward in time, subtracted from antiparticle going backward in time, because this is going from y to x, and this person's frame, y to x is y happens after x, so this is an antiparticle going backward in time. So if the person wants to interpret these quantities, they will say this is the amplitude for particle going forward in time and this is the antiparticle going backward in time, amplitude for the antiparticle going. Now we remember that what we saw and what happens under time reversal, which is the particle becomes antiparticle under time reversal. So now under time reversal, this is the amplitude of a particle going forward in time from x to y. So we have particle going forward in time x to y minus particle going forward in time x to y, and this gives 0. So this commutation relation, the causality, comes from a delicate cancellation between contributions of the particle and the antiparticle. The particle going forward in time and antiparticle going backward in time being related to each other results in this nice cancellation. Okay, so I will stop here.